Okay, I think my mic is on. You guys can hear me back there just fine, right? Yes. Excellent. So you're in for a treat. It is true that I get a little bit passionate about this kind of thing, and when I get excited, I tend to talk really fast. If I end up talking really fast like this all over here, you can't understand me, just raise your hand. I swear I will slow down. Really, I promise. And so I think we've got a good 55 minutes for me to talk you through all the things in my slides, and then we're going to have half an hour for those of you who can stick around for a Q&A. I hope you were all able to pick up a Psyche sticker at the check-in desk on your way in. At the end, when we do Q&A, I've got these lovely NASA stickers. If you ask me a good question, you might be able to earn one of these. And for those of you who are aware of the Juno mission, I've got some of those too. So audience participation will be appreciated and greatly rewarded. So here we go. I am Tracy Drain, Deputy Project System Engineer on the Psyche mission, and I'm going to talk you through the amazing things that we're going to be doing with this mission. But I'm going to start with a little primer. You guys are a great audience. I bet you know all of this stuff already. But NASA has 10 field centers across the United States. The Jet Propulsion Laboratory is over here. And that is where we do all sorts of fantastic robotic missions to explore the solar system. This is what the Jet Propulsion looks like, the Jet Propulsion Laboratory. How many of you guys have been to JPL? Yeah, see, you guys, can't wait for Q&A. So JPL is located in this lovely valley where there used to be a whole lot of nothing, because back in the 30s when they were testing rockets, they would blow up on occasion, and they wanted them out there in the middle of nowhere where no one's house or school could get damaged. And over the years, it has grown into this marvelous facility with 150 buildings, 5,500 people work there. It is amazing, and over the years, we've done, it was a little bit before I was born when it started, but the lab has conducted a series of fantastic missions to explore our world and to explore the solar system. I don't know how many of you guys recognize that, but that is Explorer-1, the United States' very first man-made satellite to go all the way around the Earth. It was launched in 1958, just behind Sputnik, and that sort of started the space race. There's Voyager, which you might recognize, that explored our outer planets, Voyager 1 and 2. Cassini, which orbited Saturn for many years and had a glorious end of mission last September. We also have astrophysics platforms, Earth orbiters, Mars rovers. There are about 24 or so missions and operations at any given time at the lab right now. So it is a fabulous place to work. So how did I wind up at the Jet Propulsion Laboratory? Well, I started off as a little baby Tracy in Kentucky, Louisville, Kentucky, and I was a giant nerd. I loved math and science. I was in the band. I was that kid. Luckily, I had a brother who's a couple of years older than I am, and he was able to fight off all the other kids to keep me from being picked on too much when I was a kid. So I got to be as nerdy as I wanted to be, which was phenomenal. I had a lovely mother, you can see where I get my smile, and she did a really great job in encouraging me to do whatever I wanted to do, to pursue whatever kind of dreams I wanted to pursue, and she bought us these great books, the Childcraft books. I should make that one come in next. But for those of you who remember printed encyclopedias, we also had printed Childcraft books to go along with them. And I remember reading the story of how scientists thought the solar system was formed and being just amazed that people could look up at the clues that they see in the world around them and come up with a theory of how the solar system came to be the way that it was. We loved science fiction of all sorts. My mom was a giant science fiction fan, the original science Star Trek, and so we watched that with her. I love Star Trek Next Generation. Of course, we watched Star Wars, Battlestar Galactica, you name it. We watched it twice. We went to the movies. We sat through it twice. And I had an everlasting love of science fiction and science fact from that. When I decided to go to college, I went to the University of Kentucky to study mechanical engineering. I have to confess, to those of you younger people in the audience, I was a little chicken to just go straight for the astronomy. I wasn't sure what I would do with an astronomy degree. We didn't have the internet back then. I'm that old. And so I chose mechanical engineering because I knew it would be a nice broad background that would allow me an in to do some kind of work in the space industry. While I was there, I had the very great fortune of landing an internship at NASA Langley Research Center. And then I went to Georgia Tech to finish up my education with a master's degree in mechanical engineering. And I was hired in at the Jet Propulsion Laboratory right out of grad school in the year 2000. I have to update my bio. It's been 18 years now. Wow. So here we are. One of the things that I love about the Jet Propulsion Laboratory is that we have so many missions going on that those of us who work there as engineers have an opportunity to explore a large swath of the solar system. I worked for 6 years on the Mars Reconnaissance Orbiter, which launched in 2005 and is still orbiting Mars now, collecting all sorts of fantastic scientific data and serving as relays for the rovers that are there. And then I spent a couple of years on Kepler, only 2 years. We launched it in 2009, and it has been really revolutionizing the way that scientists understand planets in our Milky Way galaxy. We now know that our galaxy is practically dripping with planets. If you don't know anything about Kepler's discoveries, do yourself a favor, go home, Google it, you will be amazed. And then I went to join the Juno mission in 2009. That mission launched in 2011. We had a fun-filled 5-year cruise all the way out to Jupiter, and it arrived safely on July 4th, 2016, and has been orbiting the planet now, revolutionizing our understanding about that giant planet and giant planets in general. And this year, I am moving on to a project called Psyche, and that's the one I'm going to tell you all about today. But first, a little bit of background. How are planetary systems formed? And I gotta say, even though I am an engineer, my job is engineering, I'll talk a little bit about that. I love to talk about the science because that's what the public is excited about. That's what I'm excited about. That's why I work on these missions. And because I was preparing this talk to give to you guys, I got to spend an hour one-on-one with our principal investigator, our lead scientist, Lindy L. Constantin. And she told me all the stuff I'm about to tell you. So I'm sorry, Lindy, if you're watching this and I messed something up, please go Google fact check. That's great. And you will all get a chance to learn a lot too. So this is a gorgeous image taken by the Hubble Space Telescope. Those of you who know a thing or two about Hubble images might recognize this. This is a zoomed in image of the Eagle Nebula, M16. And what you can see here is this huge, let me hit the right button, this huge molecular cloud of gas and dust, which is out there in our Milky Way galaxy, right? And this is formed by some leftover hydrogen and helium from the formation of the universe and the Big Bang, plus a lot of heavier elements that were cooked up inside of stars that went supernova and spread material out there in space. The blue color that you can see is mostly, let me not lie to you, oxygen. The red is sulfur, and the green is hydrogen and nitrogen. And you can see these gorgeous pillars of dust. These are called the pillars of creation because scientists believe that there are baby stars hidden in there that are now forming. And so how does star formation start in the first place? Scientists think that you have these huge clouds out there, very, very diffuse clouds, and then a star might go supernova nearby and put a shock wave into that cloud of gas and dust that initiates a collapse. And then the collapse continues because of electrostatic forces between the particles and because of gravity, and eventually they start to condense, and you end up with a protoplanetary disk like this one. We cannot look back in time and see the protoplanetary disk that our own solar system came from, but we can look out across the galaxy and see protoplanetary disks that are out there from star systems that are forming now. And you end up with a cloud that is collapsing, and it may have some initial angular momentum, and so it continues rotating. It keeps compressing and compressing, and you get enough compressed mass at the center to ignite nuclear fusion, and you get your star, and you have some other compressed, condensed bits of matter out around that start forming things like planets and asteroids. We'll talk a little more about that. So where did the first asteroid come from? Well, way back in 1801, this fine-looking gentleman, Giuseppe Piazzi, discovered the very first asteroid. He was cataloging stars in the sky, and one evening he found that one of the star-like objects seemed to have moved against the background. And he looked for it the next night, it had moved a little more. He looked for it the next night, it had moved a little more. Initially, he thought it was a comet, but collaborating with other astronomers, they determined that it wasn't. It was what they called a minor body. In 1802, William Herschel came up with the term asteroid, which literally just means star-like, and that's what some scientists call them. Some scientists preferred minor body, and so they called them that. And sometimes we still call them that today. And that first asteroid that he discovered was Ceres. And they had no idea what it was. That's why they just called it a star-like object. But later on, when we started to be able to look at them with radar telescopes, we got a better idea of what asteroids were. And this image is from the Dawn spacecraft, which arrived at Ceres and orbited it starting in 2015. So now we know a lot more about this one. And in fact, those of you out there might know that Ceres is no longer designated as an asteroid, but it has been redesignated a dwarf planet, just like little baby Pluto. So what is an asteroid anyway? So we talked about the protoplanetary disk, gas and dust coming together to form a star and other bodies in a solar system. Well, you start off with things coming together. The very first things were calcium aluminum inclusions. I had no idea about this. Lindy just told me all about this. And those are the very oldest things in our solar system. They can use them to date the solar system. And she said the current estimate for the solar system's age is 4.685 billion years. And as those things come together and they start gathering more and more material, you start building something that gets a bit more compressed, and it turns into this kind of rocky body here. And when you have asteroids that get broken up and that fall to Earth and make it all the way through the atmosphere and hit the ground, those are called meteorites. And chondritic meteorites, chondritic meaning it's formed of carbonaceous material, chondrules that have not been remelted since the beginning of the solar system, come from asteroids of type C. If you keep getting more and more material, you get big enough to get warm enough because of the radioactive materials that is stored in you to melt the material, and then the denser materials like metal will sink toward the middle under gravity and form something like an iron core. If this got bigger and bigger and bigger, that's how you end up with planets that are differentiated, they call it, when you have some stuff on the outside, different stuff all the way in the middle because of that whole melting, sinking process. The middle of an asteroid that's made of metal, when it runs into something and gets all broken up and you have pieces that enter the Earth, those form iron meteorites. They come from asteroids of type M. The edge between the metal core and the melted liquid metal forms this really gorgeous kind of meteorite called palisite. It has a metal matrix with these embedded gorgeous green olivine crystals in it. And the very outside forms achondritic stony meteorites, material that has kind of been processed, and it's from asteroids of type S. And you'll hear a bit more about Psyche coming up soon and why it is a very, very, very special asteroid. So what is the main belt like? There are asteroids all over the solar system. There are Earth-crossing asteroids. There are asteroids that hang out at this gravitational stable point between the Sun and Jupiter, where the gravity of those two huge bodies is kind of canceled out, and the front leading edge and then the back trailing edge of Jupiter going around and around. Those are called Trojans. You get Trojans of Mars, Earth has Trojans, but the majority of the asteroids are in the main belt, which is right here. And so exactly where is it? It is located about 2.2 to 3.3 astronomical units from the Sun. And I know sometimes when people hear AU, their brain just goes, I don't know what that is. It is a distance that's like 93 million miles, and you can think of it as your solar system's block, like a city block. I live 3 blocks from the store. The Earth is 1 block from the Sun. Mars is about 2 blocks away. The asteroid belt is from 2.2 to 3.3 blocks away from the Sun. That's where a lot of them are. And there are an awful lot of them. The total of all known asteroids is over 780,000, and that's the ones that we are aware of individually where they are. But there are more than that. The estimated number of all the asteroids in the main belt is about 1 to 2 million for asteroids that are bigger than a kilometer across. And there are millions of much smaller ones that'll probably even just be hard for us to find. Now, I used to say that my pet peeve when I was watching movies, Star Wars movies, anything out in space, was when they showed spacecraft going through the asteroid belt and you see all these asteroids, and you're like zinging to get out of the way, and I'm like, why are they doing it? It's just not like that. Asteroids are really, really far apart. On average, they were about 1 million kilometers or more between each one. So that's why we don't get that nervous when we're flying spacecraft through the asteroid belt. We have to try really hard in order to hit one. But I have to say that I've gotten over that pet peeve because I understand now when you're trying to show people what the solar system looks like, and there really are that many of them out there, that if you showed a spacecraft flying through space and you pass one lonely asteroid, no one would have the sense that you're in the belt. So okay, I get it. Storytelling purposes, fine. But just know, they're really far apart. So let's talk a little bit about Psyche, the asteroid. So we talked about the first asteroid discovery series way back in 1801. Well, in 1852, this gentleman, whose name I hope I don't mangle, Annibale de Gasparis, who was at an astronomical observatory in Italy, and he discovered his fifth of 9 asteroids that he discovered in his lifetime, and it turned out to be Psyche, which he named it. Psyche was the 16th asteroid that was discovered, and back then, for every asteroid that was discovered, they were giving it a little symbol too. So he chose to name it Psyche, who was the Greek goddess of the soul. And if you know the whole story of Psyche and Eros, she was a mortal human woman. She was married to Eros, but she wasn't supposed to look at him. And then she did one day because her evil sister tricked her into doing it. And then she ended up getting put to death. But then Eros begged the gods to make her an immortal, so they did. And now she's a Greek goddess named Psyche, of the soul. And her symbol was a butterfly wing. And so the symbol that they gave to Psyche was a little stylized butterfly wing with a star above it. So that is the asteroid that was discovered in 1852. And of course, they didn't know anything about it. It was just this star-like object, like the other ones that had been found to date. Something like this. So this is actually a picture of the asteroid. Isn't it cool? Taken from my principal investigator, Lindy L. Constantin's backyard. And if you circled any other thing in this field of view and told me it was the asteroid, I'd be like, sure. It's really hard to make out anything in that picture. So what is 16 Psyche really like? Well, it is the largest metal asteroid that we know of. It is about 280 by 230 by 190 kilometers, and there's a number in miles if your brain doesn't do anything with kilometers. It is pretty big, and I'll show you in a second what that looks like compared to things that we are familiar with. It is an iron-nickel asteroid, and the reason that they know that is by measurements they can make from the ground. They can tell that it's very high density, about the density of a bar of steel. It has a very high radar reflectivity. It has a very high thermal inertia. That's kind of how fast it takes things to cool down and warm up when they're going in and out of the sunlight. And so they think it's about 10% silicate, rocky stuff, and 90% metal. And where is it? It's out there in the main asteroid belt. It has a slightly elliptical orbit, so between 2.9 to 3.3 solar system blocks out there. And what does it look like? We have no idea. This is an artist's conception of what it might look like based on some pretty fuzzy radar images that we have. And when you look at those radar images, come back. When you look at those radar images and rotate them around, they can kind of get a sense that there's probably 2 fairly big craters. They kind of have a sense of the shape of it, right? That it has this oblong shape. But that's kind of it. So everything else you see in this image, and one that I'm going to show you later, is all kind of based on the scientific theory of how we think Psyche formed and what it sort of might look like. So this is 16 Psyche versus a bunch of other asteroids. The Dawn mission that visited Ceres visited Vesta first. And this is that asteroid. It's something like 530 kilometers across. You can see its size compared to Psyche. And then here's several other Psyche that have been studied in recent history. So it's a pretty good sized object. It's actually the 10th largest asteroid that we know of. And I think that's kind of exciting. one thing that you might not know that I didn't know until I started studying for this talk, so I can tell you all about it, is that if you take all of the asteroids in the main belt and jam them all together, you get a body that is about 4% the mass of the moon. So even though there are a lot of them out there, they're kind of small compared to the other stuff that we know about in our solar system. So here you go. Here's something you can get a sense of how big the asteroid is. We are in California, so there's Los Angeles to San Diego is about 180 kilometers. Psyche would comfortably span that distance. Our PI is from Arizona, so Flagstaff to Phoenix comfortably spans that 200 kilometers too, about the size of Massachusetts. So when you go off into your normal daily life and someone asks you what you heard about tonight, tell them you heard about a giant metal asteroid that stretches from here to San Diego. And so here's how we think this asteroid got formed. It is an extremely unique body in our solar system, and it goes something like this. You get a little planetesimal that got big enough to get warm enough so that it could melt the metal to sink down into the middle and become what we call a differentiated body. And then it has a huge collision with something, probably more than something's. Models show that it might take something like 4 to 8 collisions to knock all the outsides off. And then the metal comes back together and creates this magnetic field. Some of the outsides settle back on the top. And then maybe it froze from the outside in. Could have frozen from the inside out, we're not sure about that. But maybe it froze from the outside in, and as it's freezing, impurities in the metal start to get enriched. And they get to a point where they become kind of like an oil slick on water. They separate, and you end up with maybe sulfur-enriched impurities that are floating near the top. And as the metal shrinks, it contracts by about 7% volume, and then it cracks and releases this high-pressure liquid enriched in sulfur that spews out onto the top. Maybe some of that stuff settles onto the outer part of the asteroid, and then it must have had another collision with at least one other body that knocked it onto its side because it's rotating with its axis of rotation in the plane of its orbit. So all of these things, very, very unlikely, which is why the scientists are pretty sure there's only one object like this out in our entire solar system. And I think it's cool that the metal asteroid that we know of as Psyche today is literally the heart of a protoplanet, and it was named Psyche, which is the Greek goddess of the soul. Pretty fantastic coincidence, if you ask me. Yay. And so now on to Psyche, the mission. Psyche was proposed in the Discovery program. There's a bunch of different ways that a NASA mission can become funded and end up getting worked on and developed and eventually launched and operated. The Discovery program is one such way, and it's where NASA puts out an announcement of opportunity, a call for proposals to say, we have a cost cap of $450 million. Don't get excited about that number. If all of us, like in the United States, went out and bought a Starbucks latte, we'd have money for like 2 of those missions. And so they put out this announcement of opportunity with a cost cap, and a lot of times NASA centers partner with private industry like Lockheed Martin, like SSL, like Boeing, like Ball, and we put together these mission concepts and propose them. And it takes a long time. The people who worked on that initial step 1 proposal were at it for 2-3 years or more. And then that year, they put out these announcements of opportunity like every 2 years or so. That year, there were 28 proposals that were competing. And you go through a step 1 process, and then NASA evaluates them all, and then selected that time 5 to go forward to the step 2 proposal. And then they work on them, and they work on them, and they work on them some more. And then you hope and hope and hope and hope you get chosen. And most missions have to go through this proposal process more than once, 2, 3 times, picking up information on what they need to do the next time and what they need to do the next time. The Psyche team was really awesome and very fortunate to get selected the first time through. And they got the call from NASA in January of 2017 to be told they were one of 2 Discovery proposal missions selected that year to move on. So that's how the mission got selected. It takes a lot of people, a lot of institutions in order to make a mission like this work. And this is from the ASU website. This is just a sampling of the huge number of institutions that are participating in making Psyche happen. And I'll tell you a little bit more about a couple of them in later slides. So now we're going to spend, am I going too fast for you guys, by the way? Are you okay? So now we're going to talk through the project life cycle, just to give you a sense of how we go about from the time a mission gets selected to actually getting it designed and built and tested and operated. So we start off in phase A with a concept study, all that stuff I talked about in the Psyche proposal. You put all this information together. I think at the end, but when Psyche was selected, they had written like 2,000 pages worth of material and technical details describing it. And you're basically going, what is my concept? What are we going to do? What are my scientific objectives? And then here is a high-level description of the mission that we can make in order to go get it done. And then you enter a phase called phase B, which is where we are now, preliminary design. And you're maturing the details of your spacecraft and your instruments, your ground data system, your navigation system, all the things you need in order to make the mission real. And then sometime next year, March, April time period, we will enter phase C, which is the critical design period, where you're just fine-tuning your design and you're starting to really build your spacecraft and your instruments and your ground data system. And then we enter into phase D, which is integration. You're putting all the things together, you're testing it all, and then you're going to put it on top of a giant rocket that you didn't build and cross your fingers and launch it and hope that everything goes fine on launch day. And then you enter phase E, which is called operations. And I'll talk on the next couple of slides about what our whole journey out to Psyche is going to look like. And then more phase E, when you get all the way there, now you're in orbit around the body that you're going to visit, and you're doing your entire science ops. So let's talk through some of those things. What is it that Psyche is trying to do? What are our science questions and objectives? There are 5 different ones. Number 1, our main thing is to find out whether Psyche really is a core or if it came about some other way. We talked about the fact that it could have been frozen from the outside in, it could have frozen from the inside out, it could have been broken into a giant rubble pile and stuck back together. It could be an accretion of highly reduced primordial metal, which I don't even know what that means. But they needed to come up with a bunch of different hypotheses that could explain something like Psyche to make sure that the instruments we were putting on board the spacecraft could determine which thing it actually was. Objective B is to determine the relative ages of the surface regions. And I know that sounds really complicated, but I put a picture in here because I wanted you guys to understand that sometimes the science isn't that complicated. The way they do that is by looking at images of different parts of the surface and literally counting the craters that they see. 1, 2, 3, 4, 5, 6, and then comparing those crater counts. And then by doing that, the ones that have more craters are older than the ones that have less craters. They want to know how much sulfur, potassium, silicon is there, because even though we know it's mostly made of nickel and iron, we talked about the fact that there might be those sulfur-enriched things that spewed up on top of the surface. They want to know about that stuff. And was the formation more oxidizing and reducing? I can't really tell you what that means, but you could go online and find out. And then the last one is to characterize the topography, understand what the surface is like. When you think about craters on the moon or craters on Mars, you kind of have a visual image of what that looks like. Kind of a depression, maybe a little bit of stuff in the middle, crinkly edges. When you think about a metal body and something else coming along and striking it and maybe melting some of the metal and splashing up the metal, which will then freeze in the hard, cold vacuum of space, we don't actually know what that's going to look like. And so we've been doing experiments, firing things into metal ingots to see what the craters look like, and we're excited to see when we get all the way out to Psyche, will it look like that? We talked a little bit about that really cool palisite material that gets formed on the interface between a core of an asteroid and the mantle. Maybe the surface is going to have this beautiful glittering palisite around the asteroid. We don't know. Really looking forward to finding out. So the mission design, that's all about how we're going to get there. Here is the sun in the middle. This is the Earth where we live. There's the orbit of Mars. Psyche is out here about 2.9 to 3.3 solar system blocks away from the sun, has a slightly elliptical orbit. So we are going to launch a spacecraft from the Earth in August of 2022. It's about 4 years minus 3 weeks, minus 2 weeks is about when we're going to launch. We're going to head out on this path past Mars. We're going to do a Mars flyby to give a gravity assist in 2023. Then we're going to continue this huge looping arc all the way out to Psyche. We will arrive there in January 2026. we will spend 21 months orbiting the asteroid to the end of mission. So that's what our path to get there looks like. And here is the spacecraft. It's a pretty good sized spacecraft. This is a singles tennis court. You can see it's just a little bit longer than that, just a little less wide than that. It's got these huge solar arrays that we're going to use to power our solar electric propulsion thrusters. I just like saying that because it's a cool thing. This is the first time I've worked on a mission that isn't just chemical rockets where you take some kind of fuel and you mix it with an oxidizer and they combine and combust to produce thrust. Instead, we use xenon gas and we put a high voltage across it, insert some electrons in there to knock electrons off the xenon atoms, which ionizes them. This is a Hall effect thruster, so we use a magnetic field to accelerate things around this really cool looking thruster, and then the xenon ions get shot out the back. And they're accelerated very, very, very efficiently, so it produces very efficient thrust. It's just very low thrust. So instead of like a normal spacecraft where you would do burns once every 3 months, every 6 months, giant burns in order to correct your trajectory, we turn on our thrusters and they're on a lot of the time in order to slowly push us all the way out to where we need to be. The spacecraft is a combination of SSL, Space Systems Loral, and JPL. SSL is building the structure, the power system, the electric propulsion system, and the Jet Propulsion Laboratory is developing the avionics and the software and the fault protection. It's a really, really cool marriage because we're taking the things that SSL has done a fantastic job at for a really, really long time, building these enormous solar-powered, solar electric propulsion comm satellites around the Earth, and things that JPL has done for many, many decades, which is make very complex software that can operate autonomous spacecraft when they're way far away so that you can't just joystick them to fix them. They have to be able to take some pretty sophisticated steps when things go wrong with them. And so we're going to combine the best of both worlds and make a spacecraft that is highly capable and able to get all the way out to Psyche to do the work that we needed to do. So this is the instrument suite that we have. We have a gamma ray and neutron spectrometer, which we're going to use in order to determine the composition of elements on the surface. We have a magnetometer, which we're going to use to measure the magnetic field around the asteroid. We have imagers that we're going to use to take pictures of the asteroid so that we can understand what the surface looks like. And not shown here, but on the next page, we are doing a technology demonstration of deep space optical comm. I like to talk about that too, because it's actually using lasers to communicate with the Earth instead of the standard way we've been using radio waves. Next slide. So launch an early cruise. We're going to launch the spacecraft from Cape Canaveral, probably. We have not completely finalized that or selected a launch vehicle yet. We then, very soon after that, are going to deploy the solar arrays and check out the spacecraft and check out the instruments. That first year is going to be the prime time for demonstrating deep space optical comm, literally a laser beam from space in the near infrared. There's going to be an uplink beacon that we'll send up to the spacecraft from Table Mountain here in California, and then we're going to send a downlink from the Psyche hardware on board down to the Palomar Observatory, also here in California. When we get all the way out to the asteroid, we actually can't tell exactly where it is from the Earth. So as we get closer, we're going to use our imagers to do optical navigation to know exactly where it is as we come in. We'll start off in a fairly high orbit around the asteroid where we will be able to answer all of the science objectives related to the magnetic field detection. And then, now that we've known much better exactly where it is, we'll sneak the orbit down a bit when we will be able to answer all of the scientific objectives that have to do with what the surface looks like, the topography and the spectral imaging. We'll sneak down a bit more, and we'll use our antennas, actually our telecom antennas, to do gravity science and answer all the science objectives we have associated with that. And then finally, we sneak down to our closest orbit where our gamma ray neutron spectrometer will work the best, and we'll be able to answer all the scientific objectives related to the elemental composition. So the last thing I wanted to show you guys is this really cool artist conception video that is sort of an imaginary view of what it would look like if you were riding along behind Psyche as it came up on the asteroid. You can see some of the things we've talked about, like this orangey color, sulfur-rich material that might have been deposited on the surface, like these two craters that we can kind of tell are in the radar reflections that we see from it, like our really cool spacecraft with the solar arrays that are turning sunlight into power for everything on board the spacecraft. You can see almost here, but you can see a little bit better how there might be some giant, long bridges that are created when the asteroid was contracting, if it froze from the outside in. All of those craters that scientists will be busy counting in order to determine the relative ages of the surface. That's one of those really cool cliffs that we might see, more of the really cool sulfur material. And then as we go over the edge here, you're going to get an opportunity to see what one of those craters might look like, where you had a high energy impact that melted metal, splashed it up and maybe froze, and all these crazy spiky shapes. And then just coming into view, you might see a little bit of this sparkly olivine crystals on the surface reflecting the sunlight. So we don't really know what it's going to look like, but the scientists work with the artists to describe what we think we might see, and then they came up with really cool footage like this to kind of help us and to help people in the public grasp what the overall mission might be like. And I lied. Lastly, I wanted to talk about this really cool thing that is being done at ASU, where our PI is from, called Psyche Inspired. I think actually for the young people in the audience, they're accepting applications right now. If you want to participate in the mission, you have to be an undergrad student with any kind of major, willing and interested to create something in order to help communicate the mission Psyche to the public. And these are a few pieces of art that I picked out from the website that students who are currently participating have made. I really like this clay pot, where they have put some craters and shapes of things that you might see on Psyche. This was someone's interpretation of the goddess Psyche. This is a really cool interpretation of the spacecraft flying into Psyche. I think these are representative of the molten interior of the asteroid back when it was still molten. And this is a really cool cross-stitch pattern, actually. You can go on there and download the cross-stitch pattern if you want to and make one. I think Marla made one, didn't you? Yeah, raise your hand. Yeah. It's really cool. I like that. So it's an interesting way for people to get involved and use your creative side to appreciate the science and engineering that we're doing on this mission. No, I lied. So lastly, I wanted to make sure that you guys had all of the, or at least a handful of the websites that you could find to go get more information about the mission, to follow us along as we continue through development. There's a Twitter feed, there's Facebook, there's a blog, there's all sorts of things out there for you to go and learn as many things as you can about Psyche and be ready for the journey, launch in August 2022. I think I talked too fast. You guys have a lot of time for Q&A at the end. Hi. So I'll remind you that for good questions, you can earn yourself a NASA sticker or a Juno sticker. I'll let you pick. Did you want to announce something before we do all that?
No.
Okay, yeah, who's going to be first?
The mic around to people
Oh, good. Down in front.
How long will it take the probe to orbit around the asteroid?
Yeah, oh yes, thank you for being first. Sticker for you. We are going to be there for 21 months. Or are you asking how long it takes to go around once?
How long will it take?
I should know that. Wait. I should know that. It changes depending on what altitude we're in. Oh, I'm not going to lie. I'd have to go look it up. But I'll give you a different answer. The asteroid itself rotates once in every 4 hours. I know that one. I'm still learning, so you get me sort of new to the project. But yeah.
It was on your slide because it said how many times it went around in 100 days.
Thank you. I could bring that slide up. We could do the math real quick. Wait. See, there's Steve. He's, here we go. Okay. There you go. Thank you, Steve. Yes, back there in the hat. Oh, and there's Pickle here. Oh, shoot, I lost you. He has the mic way over there. I lied. He'll come back. Yeah.
Once the mission's complete, what is going to happen to the object that we're sending to
that is
explore?
an excellent question. So I will tell you what sometimes happens with missions, but I can't tell you exactly what's going to happen with Psyche because we don't know yet. Sometimes for missions that have a lot of fuel left over, they will do an extended mission. They could either continue orbiting longer if there's enough fuel and the navigators can work out a good trajectory somewhere else. They might go to another mission or to another asteroid. That's what happened with Dawn. I don't know if that's in the cards for Psyche, but we're not sure yet. That's something that we'll figure out once we get deep into the ops phase. Yeah. Oh, a sticker for you. I'm going to need a runner. Oh, no. Can I just give you these?
Next question. We'll go.
Yeah. He'll work his way back over here.
I didn't know. Some of the larger meteors get hotter at the center because of gravitational force. I didn't know if convection is present in larger meteors like it is on Earth.
I don't know that either. I have no idea. Sorry. I'll have to ask Lindy and get back to you. Yeah.
Okay.
Yeah.
Thank you.
Mhm. Yeah.
Yeah, previous lecturer here talked about privatization of space and how we might want to exploit the asteroids and do mining. Would this be a really good candidate for that? And is anybody looking at that
Yes.
now, going to go get the iron and nickel from it?
So let me preface that by saying I personally don't work on that stuff. I have no idea, but I love The Expanse. Do you watch The Expanse? I think that is such a great TV show. And if we're just thinking in terms of what would be worthwhile, then a giant asteroid made of metal seems like it would probably be a worthy target. But it just takes so much energy to get all the way out there, and then so much energy to get all the way back. I don't know how the pros and cons work out to whether it's actually economically feasible to go do it. If we really get to a point where we are building spacecraft out in the asteroid belt, that would be cool. I hope I live to see that. But it would certainly be a good resource, right, to get a ton of metal from. Yeah.
So, as an engineer, what does your role become as this goes
Oh yeah,
forward?
I didn't even talk about that at all,
Yeah.
did I? Thank you.
Oh,
I
yeah.
should have planted that question. Make sure you get your sticker. That is an excellent question. So as an engineer, what is my role? This is going to be a long answer. I'm sorry. So here we go. When we're building spacecraft, there are a bunch of different kinds of engineers. There are the people who might build a telecom system. There are people who might build a prop system. There are people who might work on the flight software. There are specialists in a bunch of different areas. And then you have something called a flight system engineer, where you work with all those experts to ensure that all those different things are going to come together and make a system that will work as a whole. For example, you might have, I always pick on telecom, but you might have a telecom engineer saying, I want 100 watts for my telecom system because then I can have a huge loud signal down to Earth and I will never have to worry about the Earth not being able to hear me. And then the power system might say, well, we only make 500 watts, so you can't have 20% of it. And so flight system engineers work to do those trades to figure out what is more important for the spacecraft. And then you have project system engineers who work between the spacecraft and instruments and the ground data system and the navigators and the mission design and all of that stuff to make sure that across the entire project, those huge systems are going to work together. My job on Psyche is the deputy project system engineer. So I work with the lead project system engineer in working those kinds of trades. And for example, we were recently trying to figure out whether we should, I don't know, let me see, like how many fuel tanks we should have on the spacecraft because it impacts what we do with mission design. So we were involved in working with the flight system team to figure out a trade like that. So my job evolves. One of the reasons why I really like my job is that it changes dramatically over the life of a mission. Very early on, a project system engineer or flight system engineer will be involved in those kinds of major trades. Should we do nuclear? Should we do solar? And then as you get later in the design cycle, you're making more fine-tuned trades, like how if we've chosen solar, how big do the solar arrays need to be in order to give us all the power we need? And then later, you're trying to figure out, well, now that we have our design settled down, how are we going to test this? What things can we analyze? What things can we just inspect? And then as you get later, you're going through all the processes of, well, how are we going to deploy these antennas in space? Can it be ground commanded? Does it need to be all automated? And then when you get into actual ops, things go wrong. We're really smart, but we're doing a lot of things for the first time. And it's always surprising how many little things cropped up that you didn't expect. And so then systems engineers work with the various subsystem technical experts to figure out when something happened, exactly what happened, why did it happen, what can we do about it, how do we get back on track, is it going to change anything else downstream in our mission? So that's my job in a very big nutshell. And I really enjoy it. It's a lot of fun. We're going to wear Mark out running around.
I promise I'll get to that side.
I left you plenty of time, so we can do this for a long time. Yeah. Okay. Hi.
I was wondering if maybe you could show us some of the. Actually, never mind.
No, go ahead.
Well, I was actually wondering if you could show some of the images, starting with the formation of the asteroid.
Sure. You want me to go back there? Yeah. I kind of blew through those sort of fast, didn't I? Here we go. Na. Wait for it. Oh, by the way, I have to do this. Do you see this image? Oh, no, you can't see that image. Uh-oh. Oh. Should I unplug and replug? Tech support. Unplug, replug.
That's not till tomorrow, guys. Sorry.
Yay. This is just really cool. This has nothing to do with your question, by the way, but since I was going to show my desktop, I figured I'd have to talk about it. So this is the South Pole, right, Steve? Or a South Pole of Jupiter. You can see a central cyclone here, surrounded by, oh, my picture got a little bit bigger, so you can't quite see, but there's 8 equally spaced cyclones that have this really weird symmetry to them, which the Juno spacecraft discovered as it was orbiting Jupiter. And this is infrared, so I know the colors look a little bit wacky, but it's just warmer is the bright colors, and a little bit relatively cooler are the dark colors, and that's just cool. Sorry. So we're going back to the formation of the asteroids here, there. Yeah, and I'll click through that.
You probably pressed that button.
Yeah, bet you're right. Thanks. There we go. Aha. So did you have a specific question about it, or you just want me to talk about them a little bit more?
I kind of wanted you to talk about because I kind of missed some.
Oh, sure, no problem. So, and it's good that we have all this extra time. I can totally talk about this. So this is kind of a representation of when you had small bits of dust coming together and starting to clump and form the initial phases of asteroids and planets. And then as you have more things come together and they start to get compacted under gravity, they turn into this much more stony material. And as asteroids, say it again?
How big is that?
Oh dear, I don't know. You're going to get a sticker for asking me a good question. But I think, let me see if I can channel Lindy for a second. I think she said that you need to be about 5 kilometers across before you start to get hot enough to melt things in the middle. So Google search though, fact check, make sure I'm not wrong about that. And so when things bump into each other and then break up into smaller chunks, and then eventually maybe some of them cross the Earth and then come through the Earth's atmosphere. And if you just burn up in the Earth's atmosphere, you're a meteor. We get really cool meteor showers that look like shooting stars. But if you're big enough to make it all the way down to the ground, then you're called a meteorite. And meteorites that are chondritic, which means, I think they're sometimes called carbonaceous. There's little things called chondrules, which are teeny spherical grains that they think you see in asteroids like this that weren't big enough to get a bunch of melted stuff in the middle. And you end up with chondritic meteorites on the ground that come from these type C asteroids. But when you get big enough and you have enough radioactive materials, the one thing that I should have mentioned is Lindy said when supernovas explode, they inject a lot of aluminum-26, which is radioactive, into the surrounding area. And that aluminum-26, if it comes together and forms bodies that are big enough, that's one of the elements that creates enough heat from its radioactivity in order to melt the interior. And then the stuff that's really dense, like metal, will sink under gravity to the middle. And that's how you end up with iron cores in these differentiated planetesimals, and also the iron core in our own Earth, way, way down there. We cannot go study the Earth's core because it's way too far down. You'd have to drill through, I don't know, 3,000 kilometers, and we've only been able to drill down like 12 kilometers to the point where our technology doesn't really work because it's kind of hot down there. And so if we go study Psyche, we can see something that used to be the metal core of a differentiated body, and you get when things like that run into other things, break up, and then fall to the Earth and get partially melted, you end up with iron meteorites. I don't know how many of you noticed I'm wearing little iron meteorite earrings that I got. They're not that expensive. You can buy them by the ground. It's by the gram. It's kind of cool. And I have this other really nice piece of, I think it's a Gideon meteorite, where they take it, they cut it, and then they polish it, and you can see the elongated grains in it from where it's been melted. So now that I'm on Psyche, I get to go get meteorite jewelry. It's kind of cool. Next question, Mark, I'll let you run around. And the people over here are probably going to shoot us if we don't get over here sometime.
How fast will the propulsion system allow the satellite to go?
I really should know the answer to that. I really should. I mean, where's Ted? Will you write that down? I got to keep track of these. Okay. I have no idea. I should know. But I think let me try not to lie. If you want at least a general idea, I think if you look up the Dawn spacecraft, I think our prop system is a little more efficient than Dawn's, but you can kind of get a sense. But then the Mars gravity assist is really going to increase our velocity a lot. So it's going to be a big difference between that if we had to try to get there by ourselves. I really should know the answer to that.
Tens of kilometers a second, though, relative to the sun.
There you go. Did you hear that? Probably.
Somewhere in the tens of kilometers a second, relative to the sun.
Probably.
Right, but the Earth is already zooming around. So
Yeah.
it's all relative.
Yeah. Trust him. He works at JPL too. Navigation software developer even. Yeah. Yeah.
Do you feel that the protoplanet had cooled enough to have the core become solid before the explosion that knocked the external portion away, and so that it was still intact and spherical? And was it solid at the time that the explosion that actually caused it to be formed, to have the external portion removed?
Right. And so the honest answer is I have no idea. But the follow-up answer is because every time I've seen our scientists talk about it, they've shown images like the cartoon I showed you before where it was still liquid when it had the collision, that I think the answer might be that it wasn't cooled all the way yet. But I am not sure about that. I will take that question back and ask her. Am I allowed to call on people with no mic down there? Oh, yeah, right here.
How many people are involved in the mission?
Oh, I should know that too. How many people are involved in the mission? So I think during the proposal writing process, there were at least 100 people involved. And after the proposal was selected, it's just been mushrooming and growing there. Gosh, I really should know. I'm not going to lie. A lot. Way more than that. Yeah.
I have a question up here.
Yeah. Mm-hmm.
So it's sort of a two-part question. One is the theory that Psyche is still hot inside? I'm sort of unclear at what phase it's at. Does it have a hot core?
Right, okay, no, that is a really good question. Make sure you get your sticker. Oh, you need a sticker too. Don't let Mark forget you wherever you are. So we think that it is cold now because we think that had to have happened like way near the beginning of the solar system. And so it's so small that it will have cooled all the way off. And so what we're looking for, I should have said this, with our magnetometer is a remnant magnetic field. It's not like it's still something where it has liquid sloshing around inside there. They think it would be frozen all the way through, solidified all the way through.
And so my second part is, you're calling it, they think it's a protoplanet, which would be like something that would become a planet, like.
Oh, yeah.
Is that true?
So that term, the way I'm using it, just means that it's something that, if it had kept growing, would have had the potential of becoming a planet, but it never got anywhere near big enough for that. So planetesimal, minor planet, asteroid, yeah. Oh, here comes Mark, down to you guys. Here he goes. Oh, he skipped you. No, I'm just kidding. I'm just kidding.
All right. I was kind of wondering how, like, you know how, like, the moon, well, we think the moon was formed as because, like, a giant body crushed into Earth, and it formed the ring, and then it kind of, like, became the moon. Mm-hmm. How come, like, with all the explosions of Psyche, or not explosions, but, like, collisions with Psyche, how come it didn't, like, form debris that, like, eventually became a ring?
That is an excellent question. Be sure to get your sticker. And so we know now because we've visited an asteroid that had a little baby, like little, I don't know if they call it an asteroidlet or something, a little satellite going around it. I don't know if the scientists think it's likely that Psyche could have something like that, but I don't think it's impossible. I mean, I'm an engineer, not a scientist, but there are asteroids that have little satellites, so good news. Yeah.
Thank you. Someone over here, I keep skipping.
Yeah, right there. Yeah, good. And then down here too.
I was wondering if you know how data is compressed to be sent through the beam to Earth.
Oh, do I know how data is compressed to be sent through the beam to the Earth? This is another one that I really have to know. Okay, so one thing I should be clear about is we are demonstrating the laser optical comm. That is not the way we are going to send all of our science data and all of our engineering data. We're going to use regular X-band radio for all of that stuff because we're not, since we haven't flown optical comm way deep in space yet, we are out to prove that it works, so we can't rely on it to do it. But so, let me not lie. I'm trying to channel my DSOC companions. So data in general on board the spacecraft, you can think of it as like ones and zeros. And then there are algorithms that you can use to sort of subsample. I'm making this stuff. So I know that for radio waves, you can use, when you think of normal radio when you're in a car, your amplitude and your frequency variation in order to encode data on it. I don't know how they're doing that with the laser beam, with the photons, but I'm gonna find out. But I do know that the optical comm is supposed to increase our telecom capability by like at least 10 times with the same power and mass from wherever you're sending a spacecraft to. It's pretty cool. Did you get a sticker? You did. Okay, good. Someone down.
Hi.
Nope, up there. And then down
Question.
here.
I know there's a theory that the asteroid belt was formed by one of the planet destroyed. With this mission, can we support this theory or not?
Yeah, so since we're only visiting one asteroid in our primary mission, I don't think our mission is going to say anything about that. Again, me, not scientist, but the last thing that I read was that maybe just the gravity of Jupiter and Mars prevented a planet from ever forming there in the first place. And all that material, remember, you squish it all together, you get something that's like 4% the mass of the moon, so it wouldn't have been very big anyway. I don't know how much Jupiter could have ejected over time, so I take that back. But yeah, this mission won't give us any information about that. And I'm going to talk to one person down here, and then, yeah.
So you mentioned that mining wasn't an overarching purpose of this.
Right.
So is the overarching purpose, is it to answer questions about our own core? And what types of questions do we have about our own core?
That is a good question. So is the overarching question for Psyche to answer questions about our own core? Sort of, yes. It's kind of, we want to understand what the cores of any large planets might be like, and Psyche will at least give us one data point that we can go and measure directly. I've heard our PI say, we can't reach our own core, so there's nothing we can go and see directly about it, but we can go measure Psyche, and that at least tells us something. And it's also just cool to explore a brand new kind of body. We've been to rocky worlds, we've been to icy bodies, we've never been to an all-metal world, so it's just a whole new, no one has been there before kind of regime to do. So yeah, a lot of cool science to learn from Psyche.
We have a question up here.
I take it that spacecraft, the system that's going out to Psyche, that'll be mostly put together at JPL?
Yeah, it's actually, so SSL is building the structure and the power system, but it's coming to JPL, and we're going to integrate all the instruments onto it and some other things, and then take it through all the environmental testing, all of that.
What do you think the odds are that they'll have a JPL open house where we could go up and take a look at it?
Oh, the 100%? Yeah, because we have open house, and now we call them Ticket to Explore every year. For those of you who have not visited the lab like that, the way it works now is on the JPL website, they'll announce that tickets will become available. They're all free, but you have to go and register for a ticket, because a couple of years ago, it got so busy, there were just way too many people there, so now we have to make it a ticketed event. But you really need to be there, like, with your finger hovering over the button, because they sell out, or they get all given out really, really fast. But if you go, then when you're there, you can go and look in the galleries that look over into the clean room and see the hardware that's there. We're putting together hardware for the next Mars rover right now. And as we get deeper into development, there will be a period where we'll have a Ticket to Explore event, and there will be Psyche hardware down in there. Yeah.
Most likely 2021.
Most likely 2021. Thank you, Marla. Marla's our ground data system engineer. Do you like how I threw GDS in there a couple times? Yeah, can we do one question over here in the back of there? Yes. Mm-hmm.
How many kilometers of metal are on Psyche?
Okay, I should know that. Wait. Okay, here we go. So I know, how many kilometers of metal are there on Psyche? So I know it's about, let me see if I remember the slide that I had up there, at least 170 by 230 by 280. I think if it was a complete sphere, it would be like 240 kilometers across. And I've read somewhere that if you could take the whole thing and flatten it out, it would have enough surface area to more than cover California. It would be even bigger, so it's a lot. So back over here, and then we'll go back over there, yeah? Mm-hmm.
What was the controversy about Pluto being a planet?
Thank you for asking that.
Was it an asteroid that?
Let me tell you, this is my favorite question. Get your sticker. So what is the controversy about Pluto? Here's the thing. The whole thing about Pluto, in my opinion, is a beautiful story of how science works. Science works like this. We see something we don't understand. We come up with a theory of why it's like that. We do some more measurements. We find stuff that fits. We go, oh, our theory might be right. And we find some more stuff. And yeah, theory might be right. We find some more stuff it doesn't fit. And we're like, theory's not quite right. We have to adjust it so that now it really approximates the world. You keep finding more stuff. You keep adjusting your theory. That's how we learn. That's how science works. So when you look at our solar system, you see the sun. That's all unique in our solar system. There's no other thing in our solar system like that. It's a thing. And then you have the 4 rocky inner planets. You have Mercury, Venus, Earth, and Mars. And then you have 4 giant planets: Jupiter, Saturn, Neptune, and Uranus, right? And then we have Pluto out there. And it was discovered many, many years ago. And it was a wanderer around our solar system, just like the other planets were. So, okay, that thing is like these other things. It must be a planet. And then we start learning more things. We find asteroids. We find Ceres, things that are, well, I guess we found Ceres first. But the more things we found, especially when you look out in what is now known as the Kuiper Belt object, there are things out there that are nearly the size of Pluto that seem to have the same kind of dirty snowball composition as Pluto. And we're like, wow, if we try to bin these things in categories that seem to go together, Pluto doesn't really fit in with the category of planets. And back in 2006 or so, I think it was, the scientists got together and talked about whether they needed a new kind of classification so that it now fits our understanding of all the different kinds of things that are in the solar system. And they came up with the dwarf planet classification. And Pluto goes in there, and Ceres goes in there, and several other things go in there. Who asked me that question? Where'd you go? Yes. And so that's why. And there's actually a really, really good book written by, I'm going to mess up his name. It's either Mark Brown or Mike Brown. Mike Brown, thank you. It's called How I Killed Pluto and Why It Had It Coming. And it is just as good as it sounds. It's a screamily funny read about the whole story of discovery, of finding things out in the Kuiper Belt and kind of rejiggering our understanding of the solar system. Really, really good book. It was never considered an asteroid, that's right. It went from being a planet to being a dwarf planet. Yeah. Yeah, I don't know where we're going.
Question here, and then I'll move on to that side.
Okay.
I actually have 2 questions. One of them is, why aren't you making a lander so that you can dig deeper and see what is
That
inside?
is an excellent question. A lander would be phenomenal, but a lander is harder when you go someplace for the first time. And so it's easier, even though it's not super easy, for us to send an orbiter to learn as much as we can about it. Maybe sometime, decades from now, we will send a lander to go land on it. That would be cool. I hope I live to see it. Yeah. Question number 2.
The second question is, do you think there is going to be water ice on this asteroid?
Ah, such a good question. Wow. It's so, you should all have been counting the number of times I said, I do not know. If I had to guess, like if you told me that you were going to lock the doors and I couldn't get out unless I gave you a guess, then I would guess no, engineer, not scientist, just because of the whole story of how it was formed. I have this vague intuition that when it had those huge collisions that knocked all the outside off, maybe the water would have escaped. But I really have no idea. I don't know if you guys noticed when you looked at Ceres. I'm going to go back. Na 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 la la la. Whoops. There. Come on. One more. There. That see that bright spot right there? Yeah. Scientists did not know what that was. Have you guys read up on it? Do you remember? Did we think that's water? Is that what it is? Salt? Oh, sorry. Yeah. But I don't know. It'd be interesting to find out. So we're gonna go. That's a good question. Did you get a sticker, by the way? Do you have one? Did you get a sticker? Can I have one sticker for this young lady? She asked a question a long time ago. If you asked me a question and did not get a sticker, raise your hand. Oh, right there. Right there. Can you give her a sticker? She asked a question a long time ago. Okay.
What do you know about the 2029 asteroid that's going to come with
Yeah.
18,000 miles?
Darn it, I don't know anything. Do you know anything about the 2029 asteroid? Yeah, I know. See, my mom does this to me all the time. She asks me, did you hear? I'm like, no, because I'm kind of like focused on my thing. I should do a better job following space news. But he said there's an asteroid,
2029 within 18,000 miles of Earth.
Wow.
And it's a threat.
That sounds
and
close.
If you Google 2029,
Okay.
it's like all over the place.
I will Google.
I think it's called Proteus or something like that.
I have no idea. You guys had not heard of that? Yeah, I got nothing. I will look. Thank you for the tip.
Seems that's a threat to Earth.
Yeah. I know there are a bunch of people who study near-Earth asteroids.
The trajectory is
Yeah.
supposed to change.
Yeah, so it would come out.
2036, it might be a direct hit. And it's the size of a Super Bowl.
Okay. You're like ruining everyone's evening. Yeah. There are people who study near-Earth asteroids in order to figure out. Yeah, I'll take a look now.
I get a sticker.
You do. He didn't give you a sticker? We need a sticker for that. He'll come back.
So I have the microphone.
Yes.
There
you are.
Three quick questions on the propulsion. Like, how much force does the motor generate, and how much material do you have to take to eject?
I know the answer to both those questions.
and when do you transition from chemical to electric propulsion?
Oh, what was that last one?
When you transition from chemical, which is the rocket, to...
So the first question, how much thrust do we produce? I think I read up on that one last night. I think it's about 0.06 newtons, which doesn't sound like a lot, but that's why we have to leave it on all the time. And how much fuel are we taking with us? I knew it evaporated. Somewhere a bit more than 1,000 kilograms. It's a lot of fuel that we're taking with us, but less than you would have to take if you were all chemical. And you also, what did I say? Did I say fuel? Propellant, thank you. Propellant. And when do we transition? So Psyche is never going to use chemical. It's going to be all xenon propellants, though we might use nitrogen cold gas for our attitude control.
Blast off from Earth with chemical.
Oh yeah, so the rocket that we use to blast off from Earth is definitely all chemical propulsion. But once we get released from the rocket, we are all solar electric propulsion all the way.
How long is it expected to last?
The spacecraft. So it's going to take us 3.5 years to get all the way out to Psyche, 3.4, and then 21 months in orbit. And I don't know yet what will be our life limiter. We may still have some life after that to continue or to do some other things. But that's what our design requirements are. Yeah. I don't know where the microphone is.
I have the microphone.
Yeah,
Oh, somebody just answered one of the questions, but I have one. Is there a limitation on how many craft you can track, or say JPL can track at any one time? I mean, now that with the new laser connection, maybe that is opening up another avenue, but I'm just curious. I mean,
do I know the answer to that? Let's see. How many craft can we track at one time? So we have the Deep Space Network. There is a complex with a bunch of different antennas in California. There's a complex with a bunch of antennas in Madrid, Spain. And then there's a complex with a bunch of antennas in Canberra, Australia. And gosh, I don't even remember how many antennas are at each complex. But I know that each antenna can track at least 2 spacecraft, maybe 3 I've seen at one time. 4? Is it 4?
So it depends what they have to be on different frequencies.
No, yeah.
hardware.
Yeah. So,
Do they have to rotate or something? They spend so much time.
Yeah, so usually if I'm talking to a bunch of kids, I would like drag 3 little kids up with me. I make one be the sun and then one be the earth wandering around them, right? And then rotating as they want. It makes them dizzy. And then I have another who's a spacecraft way off here. And we talk about the fact that if you're a spacecraft way over there and I'm the earth and I'm rotating, I can only talk to you now and then not now, not now, not now, now, and then not now, not now, now, which is why you want to have those complexes spread around. Like ideally, you'd have them 120 degrees apart around the equator so that as the Earth rotated, you could talk to them. They're not quite that because ocean. And so you're not exactly 120 degrees, you're not exactly on the equator, but it's pretty good. So we can keep near continuous coverage as the antennas rotate out of the way. But there are a lot of spacecraft who want to communicate with the Earth a lot of the time. And so we usually, some spacecraft like Juno, when it was on its way to Jupiter, we only communicated with it once a week, say. But then when you're doing something really important, like you're coming up on orbit insertion, well, now maybe you're going to talk to it every day or 3 times a day and like use up all, you know, the station, not all the stations, but use a station at every complex in order to do that. I think we have 24 spacecraft that are just being operated by JPL, but European spacecraft also use the Deep Space Network, and they're in different parts of the sky, depending on if you're at Jupiter, or if you're at Mars, or if you're at Saturn, used to be, or way out past Pluto, and so as long as you don't have too many spacecraft in one patch of the sky all trying to use a bunch of antenna at the same time, they work it out. And there's a whole group of people whose whole job is DSN, Deep Space Network scheduling, like who's gonna get time on which antenna when, so that we can service all the spacecraft that are out there. Yeah, I don't know the exact number, but it's a lot. Yeah. Thank you. Yeah.
Can you put up the websites again?
Yes, I can put up the websites again. Yeah. And you know, say it again.
Oh, I said there's nothing on orbit for Deep Space Network? No receivers?
Oh, there are TDRS, which stands for Tracking Data Relay Satellite. Thank you. See, I brought a posse here tonight. But I think the TDRS are mainly used for Earth orbiting assets, or assets that aren't too far out. And you end up using the Deep Space Network for things that are out past the orbit of Moon, I think. Yeah. I'm getting there. I could have hit escape, right? There you go. I don't know who had their hands up. Oh, over there. Yes, sorry, you're so patient. We'll get over there, yeah?
Just a basic question. What other countries are as advanced as us in this asteroid investigation?
Oh, gosh. What other countries are as advanced to us in asteroid investigation? Asteroid. Yeah, that's right. There was a Japanese spacecraft that visited one of the asteroids that I had up there on that one page. And then Rosetta, the European Space Agency, landed that tiny little cute rover. Rover landed on a comet, right? Yeah, so I think the Philae. Very good. Yeah. You've been very patient, and then over here. Sorry, I don't know where the mic is.
When you get to the science operations phase, do you think it's going to be confusing to have the Psyche spacecraft orbiting the Psyche asteroid?
Right? That is actually a pretty good question. I don't know where all the stickers are, but you can have one of these. So will it be, are you sure? Come on. So will it be confusing to have the Psyche spacecraft orbiting the Psyche asteroid? Well, in all of our documents, we had tried to be very careful to say 16 Psyche when we're talking about the asteroid, and then just Psyche when we're talking about the spacecraft. So I think it's not going to be confusing, but we should probably be careful about that. I don't know where the mic went. Mic? Yeah. Uh-huh.
Do you know if there's a difference between the electronic propulsion and ion propulsion?
No. I want to say that ion propulsion, when I think about ion propulsion, it means you took some kind of gas and you knocked an electron off to turn it into an ion, and then you're accelerating it out the back. And I don't know, I use electric propulsion and ion propulsion interchangeably, but you should do some Google research. That'll be your homework. Did you get a sticker, by the way?
Not one of these.
Thank you.
So normally, electric propulsion means you got the power from electricity.
Oh, there we go. Here you go.
So it would be solar electric is normally what it's called. But it could be nuclear electric propulsion.
That's true.
But no one's ever flown that, right? But it doesn't tell you how you made it into propulsion. Electric just says that's where the power came from. So it's all ion propulsion.
I'm going to give him a sticker, too.
Right.
Take that sticker. You can give it to her. Oh, you've asked a question already. We should have people who have not asked a question. Way back there.
I'm just there's
you're launching 2022.
Yes.
And arrive in
26.
In 26.
Yeah.
So, in those 4 years, what will you do?
Oh yeah. So people ask the same thing with Juno, right? We launched in 2011. You're not going to get to it until 2016. What are you going to do? Sit around, twiddle your thumbs, play solitaire, right? There are an incredible number of things that you need to do with a spacecraft and the instrument set on the way. So, for example, when we launch in 2022, we're all going to be thinking about, okay, we need the solar arrays to get out just fine. We have to check out all the instruments, check out the spacecraft. There are going to be all sorts of little things that don't go exactly the way we expect them to. So if I'm still on the mission in operations, I'd be working with a team to kind of troubleshoot and bird dog those things and get them all fixed. And we'll also know that there is a Mars flyby in front of us, and we'll all be preparing for that. And it's different with a solar electric propulsion mission, that you don't have to do like big burn every 2 months or 3 months in order to like correct your trajectory. It's the slow burn all the way out. But if something goes on with a spacecraft where it has a little hiccup and says, oh, there's something wrong with me, I'm going to turn off my thrusters for a bit, then the nav team has to go and do a bunch of analysis in order to make sure when we get the thrusters turned back on, we're back on the same trajectory. So there's like a ton of stuff to do. And we'll also be finalizing what our final operations is going to look like at the asteroid when we send a series of commands packaged up into what we call a sequence in order to take images at the right time, in order to make the spacecraft turn at the right time, to do all that sort of stuff as we're orbiting around the asteroid. So we'll be doing tons and tons of planning for that. On Juno, Steve will remember, he's our project scientist. It took us 5 years to get there. We launched, we had a year before we did 2 giant burns, and then we had another year before we did an Earth flyby, and then it was supposed to be quiet cruise for 3 years. And we were all supposed to be super bored and like go on vacation, and so much stuff happened that we told everyone that the words quiet cruise had better never come out of their mouths again. It's like, put $1 in this piggy bank whenever you say that. So I anticipate that operations is going to be very full and exciting for everybody still on the mission at that time. Yeah. Can you guys pass that back to him?
Sure.
Yeah. No, really.
Tracy, now
Yeah.
I have to ask this question, which is, you're going to do science on the way out?
Oh gosh, see, you're fired. No, I'm kidding. Are we going to do science in the way? I'm trying to channel my inner Lindy. So we have, like we did on Juno, placeholders for us to do calibrations of the instruments every 6 months. But honestly, I'm not sure how much science we can do with some of the instruments. Like our magnetometer, we'll probably be wanting to measure the solar wind, because that's going to be background when we're out at Psyche. The imager, not too much to take pictures of when you're on the way. And for the gamma ray neutron spectrometer, there's not too much to study until you get up close to a body anyway. So, yeah.
Mars flyby, there you've got an object to test and calibrate.
That's a good question. That's right. And we, those of us on the engineering side, Steve will tell you that engineers love to work with scientists, and we're not always there to just say, no, we're not going to do what you want us to do. But we love the idea of calibrating the instruments using Mars, because it's an opportunity to catch anything that doesn't work exactly the same way that we think it might. There are some complications to doing that, but it certainly seems like a nice opportunity. We'll see how things play out when we continue developing what our whole cruise ops plan is going to be like. Yeah, you should have a sticker for that. Can you get that back here? I don't know where the mic is. I better go back over here and then we'll come back. Yeah.
Okay, with the budgeting, I mean, that's always an important part of any program that you do. How close to the budget do you get?
Oh, wow.
And should we call Bank of America for a loan?
So I'm going to channel my inner project manager now. Here, we should give you the sticker. How close to the budget do we get? So our illustrious project manager, Henry Stone, a large part of his job is to make sure that the project is delivered on budget, on time, right, with all the technical things that we need it to do. And so we pay close attention to it, on a monthly basis. We talk about how we're doing, how we're tracking according to the budget. And there are things that we do, like the project manager holds what are called reserves. Like, we think the project is going to cost this much, we've budgeted for this much, I'm keeping this much over here. And so that if things overrun, I can use it in order to fix stuff here and there. And the plan is always to stick to your budget and do things. But sometimes there are surprises that you just don't have your reserves to be able to cover it. And that's when there are processes like projects going back to NASA saying, hey, we had this issue, let's explain the entire thing that happened, and can we have a little extra money to do blah, blah, blah. So that's how it works. But yeah, the plan is to be on budget, on time. Yep. Oh, wow, way back there.
I'd already asked one question, but did you say the size of the payload, the weight of the payload?
No, I did not. That is a fact I do not have locked in my brain yet. I'm sorry about that. But I think if you do...
It's a good-sized payload.
It is a good-sized payload, yeah. I think if you do a search on Google, that information should pop up. Yeah.
I had 3. Can I do 3 real quick?
Wow.
So just, I'm curious, when you go into or past that asteroid belt, if that's a concern or changes launch dates at all, or if you, as in aviation world, we just call it the big sky, small craft theory and kind of wing it?
That's
or
the
if that, okay.
Well, how did you guys remember how far apart did we say the asteroids in the belt were? 1,000,000 kilometers, yeah. So
we got some luck involved in your project. The second question. How do you prioritize, and do you give yourself leeway in that schedule of events? Like you've got the laser communication system, if it looks like that we're drawing too much power or something else, and do you just cancel that and go on? Or if at your highest orbit you're not getting what you need, are you guys stuck to that schedule of events, or do you plan?
Yeah, so we definitely do plan in margin in the schedule of events. Let's say, for example, the laser comm that we're demonstrating, it might need a certain number of sessions in order to meet its requirements. We would plan more than that in case something went wrong in any of them along the way. For example, we do that with a lot of the things that we plan on the spacecraft.
Okay, and then how do you hit the brakes once you're there? All of this slow acceleration to get there, what do you have on board to stop once you're at
Yeah, that's good. So that is a really good question. You should get a sticker for that. Can we pass that all the way back? That last one is a good one. So I will start with explaining a mission like Juno because it's kind of easier to think about conceptually. When we send a spacecraft all the way out to Jupiter and it is on a ballistic trajectory and we use our thrusters in order to just tweak it to make sure we're going to get there right at the right time, then we use the gravity of Jupiter. You need to go by the planet at the right time, at the right altitude to get captured by the gravity of the planet to get sucked into a huge orbit. That's what we do when we go visit Mars, when we go visit Jupiter and we're going to orbit them. When we go to Psyche, it's a little bit different. It does have a magnetic field, but it's not like we're going into orbit around, magnetic field. It does have a gravity field, but it's not like we're going into orbit around a huge planet. So we're using our solar electric propulsion, and when we do the trajectory design, to kind of sneak up on it, and we use it to push us into a curved orbit around the asteroid. So, yeah, I don't know where
we have
Mike
about
is.
time for one more question.
No, are people gonna fight it out? Can we do 2, please?
You could stay a little later and answer.
Okay, because I gotta get you, but over here, and then I'm coming back over there, yes.
So, follow on to that, does Psyche have enough gravitational pull to keep the orbiter in the orbit?
It has enough gravitational pull that we need to factor it into the trajectory design. I don't know how much gravitational pull it has. I'm going to go look that one up. It is pretty small. I know it is, yeah. I'm going to give you a sticker anyway. And can I cheat and just get her one question? Yes, okay, yeah.
What's your allowance from NASA?
Are you asking me how much I get paid? I'm so not telling you that. Oh, the mission. The mission was proposed under a $400 million discovery cost cap, right? So everybody in the United States buys one latte, cut that in half, that's our budget. Yeah. Yeah. I know.
Thank you so much, Tracy. We have a...
Thanks, everybody.
Thank you, Jet, for you.
Thank you.
And thank you all for your photo membership and for joining us tonight. Have a great trip home.
Thanks, guys. I can stick around a little bit for questions. My husband's going to drag me out of here not too late.